Imagine a technology so revolutionary, so world-changing that it could rewrite humanity's future overnight. A technology capable of producing nearly limitless clean energy, without radiation, without dangerous waste, without pollution, and with fuels so abundant that every ocean on Earth would become a reservoir of power. This dream has a name: cold fusion. For some, cold fusion is a scientific miracle waiting to be understood. For others, it is a failed idea, a phantom that resurfaces again and again, each time wearing a new disguise. And yet, despite controversy, failures, and decades of skepticism, the concept refuses to fade. Instead, it remains suspended on the boundary between what science allows and what science hopes for. In this calm exploration, we step into the strange, hopeful, and sometimes chaotic world of cold fusion, where brilliant minds collided, reputations were made and lost, and the impossible briefly felt within reach. We will walk slowly through the story, examining the physics, the people, the experiments, and the mystery that still lingers today. Because the truth is this: cold fusion is not merely a scientific episode. It is a profound reminder that the unknown is still vast, that curiosity is still powerful, and that the universe still holds surprises we have yet to understand. This script will guide you through 13 deep, non-repetitive sections, each exploring a unique perspective. The famous 1989 announcement and why it shook the world, the scientific backlash and the puzzle it created, the physics that makes cold fusion seemingly impossible, the experiments that keep suggesting something strange is happening, the modern renaissance, now known as LENR, the researchers risking careers to chase the mystery, and the future where this technology, if real, might change everything. This is a calm, thoughtful journey into science's most persistent enigma, a story where hope, doubt, and discovery intertwine. A story that reminds us that science progresses not only through answers, but through questions we dare to ask. Section 1. The Day the World Stopped to Listen, March 23rd, 1989. On an ordinary spring afternoon in 1989, the world's media gathered in a crowded university auditorium in Salt Lake City, Utah. Reporters expected a routine chemistry announcement, perhaps a new technique or a minor breakthrough. What they received instead was a declaration so astonishing that for a moment it felt like the future itself had shifted. Standing behind the podium were two electrochemists, Dr. Martin Fleischmann and Dr. Stanley Pons, respected, methodical scientists, not the sort of men given to exaggeration. Yet on that day, they made a claim that seemed to break the laws of physics. They announced that they had achieved nuclear fusion, but not in a star, not in a hydrogen bomb, not in a machine heated to millions of degrees. They claimed to have achieved fusion in a small glass jar on a tabletop. Fusion, the energy source of the sun, occurring quietly at room temperature, something the scientific world had declared impossible. Yet here were two chemists saying they had done it. The announcement electrified the world. Reporters called it the energy breakthrough of the millennium. Politicians spoke of a future where oil, coal, and nuclear fission would become obsolete. Environmental groups envisioned an era without pollution. Economists imagined a world where energy scarcity disappeared forever. And ordinary people, students, teachers, workers, felt the quiet thrill of witnessing history. It seemed like the beginning of something extraordinary. But why did the claim hit with such force? Because the idea of fusion is more than scientific theory. It is almost mythic. Fusion is the ultimate energy source. It powers the stars. It binds the universe together, and humanity has long dreamed of capturing it. Traditional fusion requires temperatures hotter than the core of the sun, conditions so extreme that containing them becomes nearly impossible. Billions of dollars had already been poured into fusion reactors, yet the dream remained far from reach. Then, suddenly, two chemists said they had done it, without heat, without massive machines, without radiation, and without danger. Just heavy water, a piece of palladium metal, and an electric current. It sounded too good to be true, and yet their reputations made people hesitate before doubting. Fleischmann, in particular, was considered one of the greatest electrochemists of the century. His work was meticulous, often groundbreaking. If he claimed something this extraordinary, many believed he must have something real. The days that followed were filled with excitement. Laboratories around the world rushed to replicate the results. Newspapers printed bold headlines: "Unlimited clean energy achieved. A future without oil. The dawn of a new age." For a moment, humanity felt suspended between disbelief and hope. Cold fusion, once dismissed as impossible, had suddenly become a global obsession. But beneath the excitement, something quieter and more complex was unfolding. Scientists who attempted replication encountered subtle inconsistencies. Some saw signs of excess heat, more energy produced than seemed possible under chemical reactions. Others saw nothing at all. The world watched as cautious optimism slowly turned into confusion. How could a claim so monumental yield results so inconsistent? Why did some experiments appear promising while others fell flat? The scientific community became divided, some hopeful, some skeptical, some quietly angry that such a shocking announcement had been made through a press conference instead of a peer-reviewed paper. In the months that followed, the excitement began to unravel. The U.S. Department of Energy issued a report recommending against funding cold fusion research. Many universities withdrew support. Fleischmann and Pons found themselves increasingly isolated, their reputations jeopardized. And yet, despite the backlash, some researchers quietly continued to observe strange anomalies. Bursts of unexplained heat, odd nuclear signatures, unusual material changes. These small, scattered clues prevented the mystery from dying completely. That is the story of cold fusion, a mixture of brilliance, controversy, strange results, and questions that refuse to be answered fully. But on that day in March 1989, none of that had happened yet. In that moment, the world believed it was witnessing a scientific revolution, and perhaps, in a way, it was. Just not the kind anyone expected. Because even now, More than 3 decades later, cold fusion remains one of science's most intriguing, unresolved mysteries. A phenomenon that continues to whisper, "There is something here, something you do not yet understand." ... Section 2. The Spark That Shook the World. Pons, Fleischmann, and a 1989 announcement. Imagine the world in early 1989. Computers are humming giants. Cell phones are the size of bricks. And the great scientific quests of the century seem mostly solved. Physics feels complete. Chemistry feels disciplined. Energy research feels predictable, linear, and even a little tired. And then, with the suddenness of lightning in a still sky, two electrochemists, Martin Fleischmann and Stanley Pons, step onto the worldwide stage and say something that, if true, would rewrite the future of civilization. They announce they have achieved nuclear fusion inside a simple tabletop experiment at room temperature, using materials anyone could buy. They call it cold fusion, and for a moment, the world stops breathing. A gentle beginning, two minds, one question before they became the center of global scientific controversy. Pons and Fleischmann were quiet researchers, fascinated by the subtle mysteries of electrochemistry. They were not looking for fame. They were not hunting headlines. They were, above all, intensely curious. Their starting point was beautifully innocent. Hydrogen nuclei fuse in stars. Why can't they fuse in a laboratory? Most scientists dismiss the idea entirely. Fusion requires temperatures hotter than the center of the sun. Fusion means atoms squeezed under unimaginable pressure. Fusion is violence. Fusion does not happen gently. But the two researchers wondered, what if we simply haven't been looking in the right way? What if, in the right material lattice, under the right conditions, hydrogen atoms could be so tightly confined that they might fuse? This was not a mainstream idea. It was not even a fringe idea. It was a kind of scientific romance, beautiful, improbable, yet strangely compelling. And so they began. The experiment, a beaker, some palladium, and a surprising heat. Their core setup was unbelievably simple. A glass beaker, heavy water where hydrogen is replaced by deuterium, a palladium rod, an electric current. Palladium, a rare silver metal, has a peculiar property. It absorbs hydrogen like a sponge. It absorbs so much that its structure stretches, swells, and strains. Pons and Fleischmann believed that inside those microscopic spaces, deuterium atoms might be forced so close together that nuclear events could happen. For months, they ran the experiment quietly. For months, they measured. For months, nothing made sense. The palladium rod produced more heat than the electrical power supplied should have allowed. Not just a little extra, sometimes triple, sometimes more. Too much for chemistry. Too low for conventional fusion, but unmistakably something. This was the moment when the impossible began to feel just a little possible. The decision, a public announcement that changed everything. Here is where the story becomes human. Pons and Fleischmann did not originally want to go public. They dreamed of writing a careful, peer-reviewed paper, something that would stand on its own and speak only with numbers, graphs, and method. But science is not always a quiet path. Their university worried another team might publish first. Reporters were already sniffing around. Funding discussions complicated the atmosphere. And perhaps, just perhaps, Pons and Fleischmann felt that they were on the edge of something extraordinary, something the world deserved to know. And so, on March 23, 1989, at a crowded press conference at the University of Utah, they stepped forward. Their announcement was simple, almost understated. They believed they had achieved controlled nuclear fusion at room temperature. The words drifted through the air like a breeze that slowly becomes a storm. The reaction: hope, doubt, awe, fear. Within hours, newspapers around the world lit up. Energy of the future has arrived. Fusion in a beaker. A breakthrough to end all breakthroughs. Held emergency meetings. Energy companies sent representatives. Research labs halted other projects to replicate the procedure. Investors saw visions of limitless clean energy. And scientists felt something rare. A mixture of excitement and disbelief so intense it bordered on spiritual. Because if cold fusion were real, the implications were overwhelming. Unlimited clean energy, no greenhouse gases, no radioactive waste, no need for oil, coal, or even wind turbines. A world powered by a simple tabletop reaction. Imagine powering a city with the energy from a glass of seawater. Imagine heating homes, fueling cars, traveling the world without ever thinking about emissions or scarcity. It felt not just scientific, it felt mythic. The calm before the storm. Replication attempts begin. What makes the cold fusion story so strangely peaceful at first is that for a few brief weeks, the world united in scientific hope. Laboratories from Japan to France, from Los Alamos to MIT, tried to replicate the findings. Everyone worked quietly, carefully, respectfully. There was no rivalry, no hostility, just a rare collective determination to test something extraordinary. Some teams saw hints of excess heat. Some reported strange bursts of neutrons. Some found nothing. The world waited. For a moment, uncertainty felt calming, like standing on the edge of a new continent. Not yet sure whether it contains deserts or gardens. The Pons-Fleischmann experiment had become a kind of scientific koan, simple, mysterious, and impossible to dismiss. The human side: genius, pressure, and a moment too fast. Behind the global excitement, Pons and Fleischmann were two tired men. Their lab was small, their equipment aging, and the pressure on them enormous. Every phone call felt like a demand. Every interview felt like a test. Every critique felt like a storm hitting their ship. And yet they remained gentle, soft-spoken, almost apologetic. If you watch early interviews, their voices are warm, their manner shy. They do not speak like glory seekers. They speak like men who found something strange and do not entirely understand it yet. In that quiet humility lies the heart of the cold fusion story. It was never about triumph. It was about curiosity, about two researchers standing in the doorway of the unknown, unsure whether it opened onto a new era or a dead end. A calm conclusion to this chapter. Section 2 ends in a strangely peaceful place. The world is hopeful. The experiments are ongoing. The scientists are cautious but curious. Nothing has collapsed yet. Nothing definitive has emerged. We are still in the soft twilight between possibility and impossibility, a place where science feels almost like poetry, where ideas shimmer with the delicate uncertainty of a dream. Section 3. The Great Unraveling. Replication, rejection, and the slow collapse of a miracle. The weeks following the 1989 announcement were a strange time in the world of science. Across laboratories, universities, military research centers, and quiet basement workshops, people gathered around beakers like watchers around a sacred flame. Everyone wanted to know, was cold fusion real? Was this shimmering promise of limitless, clean energy truly hidden inside a piece of palladium submerged in heavy water? In those early weeks, no one knew, and there was something peaceful in that not knowing, something calming in the shared curiosity, the global breath held in anticipation. But slowly, like mist lifting from a valley, clarity began to appear, and with it came tension, confusion, and a kind of collective heartbreak. The first cracks, when experiments refuse to behave. Science has a rhythm, a pattern, a deep, patient heartbeat. If a claim is true, the world repeats it. Other hands find the same numbers. Other eyes see the same glow. And the universe offers the same answers to the same questions. With cold fusion, the universe was quiet. Some research groups reported small glimmers, tiny bursts of heat, hints of nuclear byproducts, but nothing stable, nothing consistent, nothing strong enough to stand on. Others found nothing at all. Beakers stayed cold. Palladium rods sat still. No heat, no fusion, no anomaly. The problem wasn't that cold fusion never happened. The problem was that it happened rarely, unpredictably, like a shy creature appearing only when no one was looking. And science does not trust miracles that refuse witnesses. MIT, Caltech, and the emergence of doubt. Two of the most influential institutions, MIT and Caltech, performed highly publicized replication attempts. Their labs were bright, precise, filled with top-tier equipment and some of the most respected physicists on Earth. Weeks passed. Measurements accumulated. Numbers stabilized. And then came the reports. We see no excess heat, no consistent neutron emission, no evidence of fusion-level reactions. These conclusions traveled through the scientific world like a cold breeze. Not a storm, not anger, just a slow, settling chill. The excitement around cold fusion, once bright and warm, began to dim. Conference rooms that had been bursting with curiosity grew quieter. Scientists grew cautious in their tone. Journalists shifted their language from breakthrough to questionable claim. Hope did not vanish yet, but it began to tremble. The critics rise. Skepticism turns sharp. Science relies on skepticism. But in the months after the cold fusion announcement, skepticism sharpened into something harsher, something more emotional. Some physicists felt personally offended that two electrochemists had ventured into their territory of nuclear physics. Some believed the press conference bypassed the dignity of peer review. Some saw the global excitement as reckless. Critics pointed out flaws. The excess heat was inconsistent. Neutron measurements didn't match nuclear theory. Controls weren't strict enough. Data seemed incomplete. Each critique was like a small stone thrown into the once calm pond of possibility. Individually, none were fatal. Together, they created a landscape where doubt became the default. And the saddest part, Pons and Fleischmann were overwhelmed. Not hostile, not defensive, but simply exhausted. They had never intended to ignite a global firestorm. They had wanted time, careful analysis, quiet reflection. But science, once set in motion, moves like a river, and rivers rarely flow backward. The turning point, the American Physical Society meeting. In May 1989, the American Physical Society held a major meeting. The cold fusion session was packed. Hundreds of scientists sitting shoulder to shoulder, waiting for clarity. What they heard instead was a cascade of critiques. Results are not reproducible. No strong evidence of nuclear products. Excess heat may be measurement error. This does not match any known physical model. The tone of the meeting was not gentle. It was not curious. It was dismissive. That evening, the news headlines shifted sharply. Cold fusion, once a bright promise, was now painted as a scientific embarrassment. And yet, beneath the noise, something important was happening. Something subtle, easy to miss. A few scientists, sitting quietly in the crowd, still believed something unusual was hiding inside those palladium lattices. But their voices were small, and the storm of criticism drowned them out. The emotional collapse, from hope to humiliation. Pons and Fleischmann, once hailed as pioneers, now faced ridicule. Their funding began to evaporate. Their colleagues distanced themselves. Their university, once proud of the attention, now grew uneasy. It was as if the world had swung from one extreme to the other, from breathless excitement to sharp rejection, without ever pausing in calm reflection. At times, both researchers looked simply heartbroken. Imagine dedicating years to something strange and beautiful, believing you might have glimpsed a new law of nature, only to watch the world treat you like dreamers who mistook shadows for the sun. Their voices grew quieter, their public appearances fewer. The gentle confidence that once filled their explanations began to crumble. The world had not just turned skeptical, it had turned cold. But the mystery would not die here. Is the calming, almost poetic twist. Even as mainstream physics walked away, even as headlines mocked the idea, even as people declared cold fusion dead, a small number of researchers continued to see anomalies. Not every experiment failed. Some produced heat far beyond chemical explanations. Some detected faint signatures of nuclear processes. Some showed strange effects emerging only after weeks of loading deuterium into palladium. It was inconsistent. It was fragile. But it was there. It was as if nature were whispering instead of shouting. Most people stopped listening. A few leaned closer. A soft ending for a hard chapter. Section 3 ends in a quiet place, a contemplative place. The world has largely turned its back on cold fusion. The scientific storm has passed. The excitement has faded into skepticism. But the mystery itself remains, because science does not close its doors forever. It does not erase anomalies. It simply waits, sometimes patiently, sometimes impatiently, for better tools, better theories, better understanding. And beneath the surface of rejection, a small ember of curiosity still glows. Cold fusion had not been disproven. It had simply become unresolved. A gentle question floating in the space between possibility and impossibility. Section 4. The Quiet Persistence, How Cold Fusion Refused to Die, 1990 to 2000. As the 1990s began, the world believed the cold fusion story was finished. Newspapers moved on. Research funding evaporated. Most physicists went back to their routines, filing cold fusion alongside perpetual motion machines and forgotten scientific curiosities. But in the quiet corners of research labs and university basements, something surprising was happening. Cold fusion wasn't dying. It was settling. It was becoming smaller, quieter, yet strangely more resilient, like a flame that refuses to go out, even when shielded from the wind. This is the story of that unexpected persistence, the comfort of working in the shadows. When the media spotlight faded, a kind of calm returned to the field. Gone were the journalists, rushing to press releases. Gone were the explosive headlines predicting an energy revolution. What remained were the scientists who had always been there for the curiosity, not the fame. These researchers were meticulous, patient, fascinated by anomalies, comfortable with uncertainty. Most of them weren't trying to defend Pons and Fleischmann. They weren't even trying to prove cold fusion real. They were simply drawn to something strange. Tiny patterns in the data that didn't make sense but kept appearing, just often enough to demand attention. There is something soothing in this kind of science, the slow, patient work of noticing. Japan steps in, the birth of a national program. While American support evaporated, Japan took a different path. Curious about the early anomalies and aware of Japan's long-term energy challenges, several major institutions quietly began studying the phenomenon. Toyota, Mitsubishi Heavy Industries, Osaka University, the Japanese Ministry of International Trade and Industry. These weren't fringe groups. These were pillars of Japanese science and industry. Their approach was methodical, cautious, and dignified. They didn't use explosive claims. They didn't chase headlines. Instead, they simply asked, why do some experiments show unexplained heat? In time, Japanese researchers reported something unusual. In certain nickel-based systems, subtle changes in isotopes seemed to appear. Tiny nuclear shifts that chemical reactions could not explain. The world largely ignored these findings, but for those paying attention, it was a sign. The story was not over. A new name for an old mystery, LENR, in the mid-1990s. Researchers realized the phrase cold fusion had become a burden. It was emotionally charged, politically complicated, scientifically controversial. So they chose something quieter, something neutral, something that didn't promise more than it could deliver. Low-energy nuclear reactions, or LENR. a name that did not claim to rewrite physics, a name that did not provoke skeptical anger, a name that simply described an observation. Nuclear-like effects appearing at temperatures far lower than standard fusion. The shift was subtle but powerful. It allowed researchers to breathe again, and slowly the stigma began to soften. Unexpected heat, the return of the anomalies. Even as mainstream institutions stepped back, small but credible experiments kept producing hints, tiny fingerprints of something nuclear happening where it shouldn't. Typical observations included heat bursts lasting minutes to hours, temperature rises far above chemical limits, isotope shifts that matched nuclear pathways, occasional faint emissions consistent with weak nuclear reactions. These events were not dramatic. There were no glowing reactors, no runaway reactions, no publicity stunts. Instead, there were quiet labs, controlled experiments, data sheets filled with puzzling numbers, researchers who wore expressions of patient curiosity, not triumph. One scientist described the process like tending a garden. You do everything right, and sometimes nothing happens. Other times, a flower blooms unexpectedly, and you just observe it. That calm, contemplative mindset became the heartbeat of LENR research. A strange catalyst, the role of deep loading. One of the reasons early cold fusion experiments failed was simple. Most teams didn't realize how difficult it was to force deuterium into palladium. Palladium is like a sponge, but not a simple one. It must be coaxed, slowly, carefully, precisely. In the mid-1990s, researchers discovered that the anomalies, especially excess heat, appeared only when palladium was loaded with deuterium to an extremely high ratio. This process could take weeks, sometimes months, and it required flawless crystal structure, precise temperature control, perfect electrical conditions, delicate patience. If the loading was even slightly imperfect, nothing happened. This explained why early replications had failed. It also meant that cold fusion wasn't magic. It was sensitive, fragile, and highly specific. Knowing this restarted the field. Dozens of labs recalibrated their methods. New experiments began with the same gentle, careful attention one might give to growing a rare plant. And the anomalies appeared more often. Not consistently, not predictably, but undeniably. Government eyes turned back, quietly. Even though cold fusion had fallen out of public favor, several governments quietly kept an eye on the data. Energy independence is a powerful motivator. Nuclear anomalies, even tiny ones, are interesting. During the late 1990s, classified and semi-classified interest emerged from the U.S. Navy, DARPA, the Department of Energy, NASA researchers, Russian Academy of Sciences teams. None of these groups publicly endorsed cold fusion, but none dismissed it entirely either. Their internal stance was often the same. Something odd is happening. We cannot ignore anomalies. This was not the loud confidence of a breakthrough. It was a calm, steady curiosity, a desire to understand a puzzle rather than declare a conclusion. The return of Fleischmann and Pons, quiet but persistent. While mainstream science had turned its back on them, Pons and Fleischmann continued their research in France, funded quietly by a Japanese corporation. They worked away from the noise, away from criticism, away from the media that had once celebrated them and then turned on them. In this atmosphere of calm isolation, they refined their methods. And again, they saw excess heat. Subtle, controlled, but unmistakable. But they no longer chased recognition. They sought understanding. And there was something deeply peaceful in that. A field transformed from miracle to mystery. By the end of the 1990s, cold fusion had changed. It was not a revolution. It was not a failure. It had transformed into a mystery, quiet, persistent, and strangely beautiful. It existed in a twilight zone between acceptance and rejection, between possibility and impossibility. And that in-between space is where some of the most interesting science often lives. Section 5. The Strange Signals. When experiments whisper instead of shout. Cold fusion's deepest mystery is not found in dramatic explosions or spectacular energy surges. Instead, its story is shaped by something gentler, almost fragile. The quiet appearance of tiny, puzzling signals that show up only when the experiment is treated with patience, precision, and a sort of scientific calm. This section is about those signals, subtle, faint, yet persistent enough to make scientists stop and wonder whether something genuinely unusual is taking place beneath the surface. The quiet lab where nothing happens until it does. Imagine a laboratory in the late 1990s, a small room filled with stainless steel benches, a few instruments humming with soft electrical tones, and a researcher sitting with a cup of lukewarm coffee, staring at a set of numbers that never seem to change. Most days, experiments produce nothing of interest. No excess heat, no strange emissions, no anomalies, just silence. But then, occasionally, maybe once every 40 or 50 runs, something shifts. A temperature curve bends upward. A reading drifts out of its usual range. An instrument reports a tiny spike in energy, just beyond chemical explanation, but far too small to call a breakthrough. The researcher doesn't jump up in excitement. There is no headline moment. Instead, there's a slow exhale, a quiet acknowledgement. There it is again. This delicate, almost meditative pace became the hallmark of LENR research. Why the signals are so hard to capture. One of the major reasons cold fusion remained controversial is simple. The signals were never loud. They were faint. They came and went. They defied easy replication. Scientists eventually realized that the anomaly depended on dozens, maybe hundreds, of microscopic factors. The grain boundaries inside the palladium, tiny imperfections in the metal lattice, the exact ratio of deuterium inside the structure, temperature drift over hours or days, pressure fluctuations as small as a breath, the age of the electrode, even the purity of the water used. In traditional nuclear physics, such fragility is unusual. Fusion is supposed to be violent, energetic, impossible to miss. But LENR isn't explosive. It's delicate, closer to whispering than shouting. This fragility confused researchers. It also intrigued them, because in science, when something is incredibly difficult to reproduce, yet still manages to appear often enough to tease you, it usually means you're close to a real phenomenon, one you simply don't understand yet. The most mysterious signal: excess heat that shouldn't exist. The central clue in the LENR puzzle is excess heat that does not match chemical limits. Chemical reactions have strict upper boundaries. You can calculate exactly how much heat a known substance should produce under specific conditions. But in certain experiments, researchers recorded small bursts of heat lasting from minutes to days, smooth, continuous warming that couldn't be traced to any chemical source. A gradual rise in temperature without any apparent catalyst. Energy outputs far greater than the energy used to run the experiment. The amounts were modest, usually the equivalent of a few extra watts. Enough to warm a cup of tea, not enough to power a city, yet far too large to ignore. In some ways, this small scale made the phenomenon more credible, not less. Huge energy surges would suggest an error. Tiny, consistent anomalies suggest the physics is subtle, not flawed. Unexpected helium, a nuclear fingerprint. One of the most intriguing signals came from trapped gases. In certain successful experiments, researchers found helium-4, the same isotope produced by known nuclear fusion reactions. Crucially, the amount of helium correlated with the amount of heat. No helium appeared in control experiments. Helium showed up only when deuterium-loaded palladium produced excess energy. Helium levels matched what would be expected if nuclear reactions were taking place on a very small scale. Helium is extremely difficult to fake. It does not sneak into sealed systems. It does not form in chemical reactions. So when helium appears where it shouldn't, something nuclear is happening. This was one of the strongest hints that LENR was not just an experimental fluke. Strange particles, signals that come and go. Some labs reported bursts of rare, low-level particles, soft X-rays, low-energy neutrons, unusual electromagnetic pulses, shifts in isotope ratios. These emissions were always faint, brief, inconsistent, far too small to be dangerous. Yet they were also nuclear in character, energy carrying, correlated with other anomalies. It was as if the experiment wanted to reveal something, but only in glimpses, like lightning flashing behind clouds. A flash here, a pulse there, never enough to prove anything outright, always enough to raise questions. The beauty of anomalies, patterns in the noise. When dozens of labs around the world report dozens of different anomalies, science begins to search for patterns. Over time, researchers noticed excess heat often occurred during the transition between stability and instability, not at steady-state conditions. Slight temperature changes could trigger or shut down the effect. Electrical currents sometimes acted as catalysts. Pressure fluctuations could start a reaction that lasted for hours. Cracks forming inside the palladium seemed to play a role. None of these patterns were clear. None of them guaranteed success. But they were not random, and in science, the existence of a pattern, any pattern at all, is enough to justify continued exploration. Why these signals still matter today. The faint signals of the 1990s were not enough to declare a technological revolution, but they were more than enough to keep the field alive. They told researchers several important things. There is something happening that cannot be explained by chemistry alone. The phenomenon is real but fragile, dependent on subtle conditions. Nuclear effects may be possible in condensed matter in ways we do not yet understand. The door to new physics might be narrower than expected, but it is not closed. Cold fusion did not thrive because it produced spectacular results. It survived because it produced persistent ones. Anomalies that refused to disappear. Heat that appeared when nothing should happen. Helium that arrived without explanation. Signals that flickered like stars behind a fog. It wasn't a roar. It was a whisper. And for the scientists who listened carefully, that whisper was enough. Section 6. The metal that remembers, how palladium became the heart of the mystery. If cold fusion had a main character, a central figure around which the entire mystery quietly revolves, it would not be a scientist, nor an equation, nor even a device. It would be a metal, a soft, silvery, unassuming element called palladium. At first glance, palladium seems ordinary. It's used in jewelry, electronics, and catalytic converters. It tarnishes slowly. It is gentle to work with. But beneath its calm surface, palladium hides an astonishing talent, one that turned it from a mundane metal into the centerpiece of one of the most debated scientific puzzles of the last century. Palladium can absorb hydrogen like a sponge absorbs water, not just a little, but remarkable, almost impossible amounts. It can hold hydrogen inside its structure until the two become inseparable, like breath dissolving into lungs. And in the process of absorbing that hydrogen, when the conditions are just right, when the temperature and pressure dance in precise harmony, strange things begin to happen. Things that should be impossible, but they do not happen loudly. They do not erupt like fireworks. Instead, they unfold softly, quietly, like something secret taking place beneath the surface. This section explores how palladium became the material at the center of cold fusion's most intriguing moments. Why palladium? The unusual gift of absorption. Palladium can load itself with hydrogen to an extraordinary ratio, up to 900 times its own volume. This is not normal behavior. Most metals can absorb a little hydrogen. A few can absorb moderate amounts. But palladium becomes saturated so deeply that the hydrogen atoms line up inside its crystal lattice like rows of tiny guests seated at a perfectly arranged banquet. When deuterium, the heavy form of hydrogen, is used instead, the effect becomes even more fascinating, because every deuterium atom carries the potential for nuclear interaction. But those interactions only occur when the metal is nearly fully saturated. The atoms are packed incredibly close together. The lattice develops microscopic strains. Deuterium begins to behave less like gas and more like something trapped, confined, and pressurized from all sides. Within this confined space, deuterium atoms are squeezed together, gently, silently, but relentlessly. It is this environment that some researchers believe may trigger the tiny, soft, almost ghost-like nuclear events that define LENR. Not explosions, not plasma, but quiet, low-level processes that unfold inside a solid where the atoms have no room to run. A lattice under stress, when order creates chaos. Inside palladium, hydrogen does not simply sit in place. It pushes, it strains, it warps the lattice like breath stretching the walls of a balloon. This stress is essential. Without it, no anomalies appear. With it, the metal becomes something like a living structure, its atoms shifting, its surface cracking in microscopic patterns, its internal geometry bending into shapes that favor unusual interactions. Scientists began noticing that LENR signals, excess heat, helium, strange emissions, often appeared when the palladium lattice was under maximum stress. Cracks were forming. The material was nearly collapsing. The deuterium loading ratio approached perfection. It was as if the metal needed to be pushed to its limit before it revealed its hidden behaviors. This idea led to one of the most striking observations in LENR research. The anomalies don't arise from stability. They arise from the edges of instability. The metal performs its strangest tricks right at the threshold of failure. Microscopic cavities, the hidden rooms inside palladium. As palladium saturates with deuterium, tiny nanoscopic cavities form inside it, bubbles that no human eye can see, pockets of clustered atoms held under unimaginable pressure. Some scientists theorize that these cavities act like natural particle traps, forcing deuterium atoms into close proximity in ways that normal physics rarely allows. Inside these tiny, high-pressure pockets, the electrons may behave differently. Screening effects may reduce repulsion. Atoms may approach each other closer than usual. Exotic quasi-nuclear interactions might become possible. This isn't the violent fusion of stars. It's something quieter, something shaped by geometry, confinement, and the intimate arrangement of particles. A nuclear reaction not born of heat, but of space, or rather, the lack of it. When palladium cracks, the story deepens. One of the most surprising findings was that microcracking, a sign of stress, fatigue, even damage, often triggered the LENR effect. To most researchers, cracks mean failure. But in cold fusion, cracks meant possibility. The moment a crack forms, the lattice shifts. New surfaces appear. Atoms rearrange themselves suddenly. Local pressures spike. Cavities collapse and reform. These transitions, brief and delicate, create the ideal conditions for anomalies to emerge. It was as if palladium, in breaking down, briefly fell into a configuration that nature rarely produces. In those moments, something unusual slipped through. This realization turned LENR into a field obsessed with surfaces, imperfections, texture, and aging. Fresh palladium rarely worked. Old, battered, stressed palladium often did. The metal had memory. It behaved differently after long use. It was learning, changing, gaining character. This was not chemistry as scientists knew it. This was something else. The unpredictability problem. Palladium is temperamental. For all its potential, palladium is notoriously inconsistent. Two pieces from the same batch behave differently. Two identical setups produce different outcomes. A metal that worked 1 month may refuse to work the next. These inconsistencies frustrated scientists. They fueled skepticism. They slowed progress. But they also revealed something profound. Cold fusion is not a reaction. It is an environment shaped by atomic arrangement, lattice strain, microcracks, impurities, local geometry, age and history, subtle changes in temperature and pressure. Every palladium sample is a unique universe with its own landscape of stress and structure. This made replication difficult, but it also made the research more intriguing. Because when a phenomenon depends on delicate conditions, it often means the phenomenon is real, just fragile. Why palladium remains at the center of the mystery. Even after decades of research, palladium continues to be the material where LENR is most frequently observed because of its extraordinary absorption, its ability to host hydrogen densely, its tendency to form stress patterns, its receptive, flexible lattice, its peculiar electronic structure. Palladium is, in many ways, the perfect playground for a new kind of physics, one that sits at the border of nuclear and condensed matter science. And so, scientists continue to return to it, to stress it, to crack it, to load it and unload it, to invite it to reveal its secrets. Sometimes it answers, quietly, subtly, but undeniably. Section 7. The experiments that shouldn't have worked, but somehow did. There is a quiet category in the history of science, experiments that simply should not have worked. Not because they were poorly constructed, or because the scientists lacked skill, but because the experiments appeared to violate rules of nature so fundamental that their success seemed like an illusion. Cold fusion belongs to this special category, sitting beside curious anomalies like superconductivity before it was understood, ball lightning before it was photographed, and the mysterious early successes of quantum entanglement experiments, when most scientists thought such results must be experimental noise. To appreciate why certain cold fusion experiments caught the attention of the scientific world, we must return to the mindset of researchers after the original Fleischmann-Pons announcement. Many scientists expected immediate failure when they attempted to replicate the results. They did their job carefully, meticulously, even with a hint of skepticism that sharpened their senses, but nearly all believed they already knew what the outcome would be. Nothing. No heat, no excess energy, no reaction. And yet, in a few isolated labs, scattered around the globe, like quiet points of light in the dark, experiments produced results that did not fit the established narrative. These were not sensational claims shouted at press conferences. These were private moments, scientists standing in front of instruments, blinking in disbelief, or staring at charts that seemed to whisper, "Something is happening." Let's gently walk through a few of the most intriguing cases. The unexpected heat bursts, one of the earliest curiosities, came from researchers who noticed irregular bursts of excess heat. Unlike the sustained, long-term heating that Fleischmann and Pons had claimed, these bursts were sudden, brief, and unpredictable, like lightning flashes inside the world of electrochemistry. Imagine setting up an experiment expecting nothing but predictable behavior, only to see a temperature spike that rises faster than any known chemical reaction could justify. Not enough to power a city, not even enough to boil a small pot of water, but enough to be unmistakably real. Some scientists describe these bursts almost poetically, like a hiccup from the system, as if the material momentarily exhaled energy, a whisper of something we cannot yet name. These small, unexplainable pulses didn't prove cold fusion, but they refused to disappear. Even when labs tried different metals, different electrolytes, or different setups, the occasional heat burst returned. It was like a rare visitor knocking on the door, too quiet to understand, too persistent to ignore. Helium where helium should not be. Another mysterious pattern emerged from experiments designed to detect nuclear byproducts. Normally, helium, especially helium-4, should not spontaneously appear in a sealed electrochemical cell. Helium does not react chemically, does not spontaneously form under normal conditions, and does not seep easily through metal containers. It is one of the most stubborn inert gases known. Yet in a handful of experiments, researchers detected helium-4 at levels significantly above the background environment. Intriguingly, the helium seemed to correlate with periods of unexplained heat. Not noise, not random, not inconsistent. It didn't require much helium to raise eyebrows, just trace amounts. But in science, traces can be everything. A trace can rewrite an entire equation. To many conventional physicists, this was the strangest puzzle. Heat is confusing, but helium is unforgiving. If helium is truly being created in these systems, something nuclear is happening. And something nuclear happening at room temperature breaks the rules, or at least the rules as we understand them. Some scientists privately admitted that if not for the stigma surrounding cold fusion, the helium results would have inspired deeper, more open investigation. Metal lattices showing scars. Another set of anomalies came not from heat or gases, but from the materials themselves. After certain experiments, the metal used, often palladium, showed unusual features, microscopic pits, as if tiny explosions had occurred, unexpected structural changes, clusters of isotopic irregularities. These changes were subtle, nothing visible to the naked eye, but under a scanning electron microscope, The metal surfaces looked strangely wounded, as if small, localized bursts of energy had reshaped the crystal lattice. Some researchers compared the patterns to miniature crater fields. Others described them as thermal scars. And again, these marks appeared in experiments where unexpected heat had been observed. The marks did not prove cold fusion, but they hinted at unusual stresses, unusual reactions, and perhaps unusual energy densities at extremely small scales. In a field dominated by controversy, these tiny scars became small but powerful questions carved into the surface of reality. The consistency that shouldn't have existed. One of the most fascinating meta-observations came from systematic attempts to repeat cold fusion trials. Even though most experiments failed to replicate Fleischmann and Pons's original claim, the few that did succeed tended to succeed under surprisingly similar conditions. Extremely high hydrogen loading ratios, particular crystal structures within the metal, long periods of incubation, very slow, carefully controlled current application, high material purity. This did not look like pure chance. Pure chance produces noise. Pure chance produces chaos. But this looked like a pattern, an elusive, fragile one, but unmistakably a pattern. It suggested that something might be happening, but only in very specific, very narrow circumstances, much like superconductivity, which only appears below certain temperatures and after decades of chasing the conditions that enable it. Cold fusion might require a similarly finicky setup. A few researchers have compared it to trying to grow a rare orchid. Yes, it can bloom, but only when everything is perfectly aligned. The uncomfortable middle space. The peculiar thing about these anomalies is that they are not strong enough to overturn physics, but they are too stubborn to dismiss. They live in a scientifically uncomfortable middle zone, like faint signals from a distant lighthouse, visible only when the night is calm. Science dislikes uncertainty, but nature often whispers before it speaks clearly. And the whispers around cold fusion have never fully faded. This doesn't prove the phenomenon is real, but it does prove that the world is more complex, more delicate, and more unpredictable than our models sometimes allow. And so in this section, we rest in that space, the space of experiments that modestly tap on the door of the impossible, hinting that perhaps we do not yet know the full map of the forest we are walking through. Some experiments should not have worked, yet a few of them did. And it is in that contradiction that the story of cold fusion becomes most intriguing. Section 8. The quantum possibilities. When the very small changes everything. If cold fusion has a natural home anywhere in physics, it is in the strange and delicate landscape of the quantum world, a place where intuition falters, where logic curves in unexpected directions, and where the rules of everyday life dissolve into something more fluid and mysterious. Most of the arguments against cold fusion rely on classical physics, the idea that two positively charged nuclei should repel each other with overwhelming force unless given enormous amounts of heat and pressure. This is correct, at least in our familiar world. But classical physics is only half the story. The other half lies in quantum mechanics, where certainty dissolves into probability. Particles act like waves, and boundaries soften into gradients. Some researchers believe that the key to understanding cold fusion, if it exists at all, might lie hidden in the quantum behaviors of hydrogen inside metal lattices. And so, in this section, we approach the possibility gently, not as a claim, but as a quiet thought experiment. What if the quantum world is doing something subtle, something unexpected, something we have not yet learned to measure? Let us explore the possibilities with calm curiosity. The metal lattice as a quantum world. A block of metal may look solid and rigid, but at the atomic level, a metal lattice is not a static structure. It is a dynamic, vibrating environment, atoms oscillating, electrons drifting freely, microscopic spaces shifting, shrinking, and expanding like the breath of something alive. Hydrogen inside this structure behaves differently than hydrogen in a gas or liquid. When hydrogen atoms enter the lattice, especially palladium, which is known for absorbing remarkable quantities, they do not remain whole atoms. They shed their electrons, becoming bare protons embedded within a sea of electrons that move throughout the metal. In this environment, the hydrogen nuclei exist not as individual, isolated points, but as quantum wave packets with shapes, positions, and energies constantly fluctuating. This is where the classical picture begins to break apart. Classically, two protons repel each other with enormous force. Quantum mechanically, the situation is far more nuanced. Quantum systems allow for tunneling, the ability for particles to pass through energy barriers they do not have the energy to overcome. They allow for overlapping probability distributions, for collective excitations, for emergent behaviors that arise only when large groups of particles interact. What if, inside a metal lattice, hydrogen nuclei begin to behave collectively instead of individually? What if their wave functions overlap? What if their distribution fluctuates in subtle ways classical models cannot predict? This is not a declaration. It is an open question, one that some physicists believe deserves deeper exploration. Quantum tunneling, a door through the impenetrable. Quantum tunneling is one of the strangest gifts nature offers. It allows particles to do what seems impossible, to appear on the other side of a barrier without ever going over it. Tunneling is the reason stars shine. It is the reason radioactive decay happens. It is woven into the fabric of the universe. If tunneling plays a role in cold fusion, it would not be shocking in principle. Tunneling enables nuclear reactions inside stars at temperatures that classical physics says should be far too low. But even with tunneling, the probabilities are incredibly tiny at room temperature. Yet, if the metal lattice enhances the chance of tunneling even slightly, perhaps through compression effects, resonance modes, or coherent interactions, it could change the picture. Some theories suggest that under the right conditions, hydrogen nuclei might resonate collectively like a choir singing in perfect harmony. When particles vibrate collectively, new pathways can emerge, pathways that simply do not exist when particles act alone. Imagine dozens, hundreds, or thousands of protons vibrating in synchrony inside tiny pockets of palladium. Imagine wave functions aligning, intersecting, reinforcing, creating rare moments of intense, localized density. It would not need to happen everywhere. It would not need to happen often. It would only need to happen occasionally, in rare, almost ephemeral flashes. This could explain the strange, small, unpredictable bursts of heat seen in some experiments. Not proof, but possibility. Coherence, the quantum key to the impossible. Coherence is the secret ingredient in many quantum miracles. It is what allows lasers to exist, superconductors to function, and superfluids to flow without resistance. Coherence is when many particles behave not as individuals, but as a single, unified entity. Their waves align, their states interlinked. Normally, coherence is fragile. It breaks easily under thermal noise, but in some materials and under specific conditions, coherence can persist at higher temperatures than expected. If hydrogen inside a metal lattice could enter a coherent state, even briefly, the fusion barrier might shift in ways classical models cannot predict. The idea is speculative. No experiment has confirmed quantum coherence in hydrogen-loaded metals at the necessary scale, but physics is full of surprises. It took decades before scientists realized that electrons in certain materials could form coherent pairs and flow without resistance at temperatures far above absolute zero. What seems impossible often turns out to be simply misunderstood. The zero-point puzzle. Zero-point energy is the lowest energy state allowed by quantum mechanics. A subtle, ever-present vibration even in perfect vacuum. It is the hum of existence, the faint rippling that never fully fades. Some fringe theories, approached cautiously but not dismissively, propose that interactions between hydrogen nuclei in a metal lattice might tap into or resonate with zero-point fluctuations, not as a source of unlimited energy, but as a subtle enhancement to tunneling probabilities or nuclear interaction rates. Most physicists view this idea skeptically. It borders the edge of what is currently measurable. And yet, the history of physics contains many examples where the vacuum, once thought to be empty, revealed hidden structure, from virtual particles to the Casimir effect. The vacuum is not nothing. It is a stage full of invisible actors. Whether they play any role in cold fusion remains unknown. A universe where the very small shapes the very possible. Quantum mechanics reminds us that nature does not always obey our expectations. It does not need our permission to behave strangely. The microscopic world is full of surprises, and many technologies that once seemed impossible, lasers, transistors, MRI machines, emerged precisely because someone dared to look closely at the quantum realm. If cold fusion ever becomes real, it will not look like a miniature version of the sun. It will not resemble classical nuclear physics. It will emerge from the quantum world, quiet, delicate, barely measurable, and astonishing. And perhaps somewhere in the overlapping wave functions, the synchronized vibrations, the fleeting moments of coherence, the universe is whispering a hint. The rules are deeper than you think. Section 9. The experiments that refuse to behave. Strange signals, elusive heat, and the puzzle of reproducibility. For most scientific fields, progress is built on clarity, a hypothesis, a method, an experiment, and a result that anyone, anywhere, can reproduce. But cold fusion does not live in this world of clean lines and simple outcomes. Instead, it exists in a shadowy in-between space, a place where results flicker like distant candle flames, appearing unexpectedly, vanishing just as unpredictably, refusing to settle into a pattern that the scientific community can comfortably accept. In this section, we slow down and walk through that landscape, the confusing, fascinating archive of cold fusion experiments that seem to work, and yet somehow never behaved reliably enough to convince the world. This is not a place for claims. It is a place for curiosity. The first glimmers, fleeting heat in a quiet laboratory. After the dramatic 1989 announcement by Martin Fleischmann and Stanley Pons, hundreds of laboratories tried to replicate their results. Most found nothing unusual, but a small number reported strange, sometimes unexplainable signals, pockets of excess heat, odd bursts of helium, unusual radiation spikes, and other anomalies that did not fit existing models. These signals were irregular. They were subtle. They were frustratingly non-deterministic. Yet they were there. Not all the time, not everywhere, but often enough that respected scientists wondered, are we missing something important? One of the earliest puzzles arose in labs where Palladian samples absorbed hydrogen extremely quickly. The tiny metal lattices appeared to swell, distort, and sometimes crack. In these strained conditions, researchers occasionally detected small but measurable increases in temperature. Increases too large to be explained by known chemical reactions. Yet when they repeated the experiment, everything would return to normal. It was like trying to catch fog with one's hands. Helium, a whisper of something nuclear. Among the most intriguing clues came from experiments that detected helium-4, the same helium isotope produced by fusion inside stars. The quantities detected were extremely small, almost ghost-like, yet disproportionately large compared to any chemical explanation. But the results were inconsistent. Some experiments found helium, others found none. Helium measurements are notoriously difficult. It diffuses through barriers. It contaminates easily. It hides quietly inside imperfections in metal. And yet, in a few well-documented cases, researchers reported a correlation between excess heat and helium-4 production, as though, in brief moments, microscopic fusion events were leaving behind faint fingerprints. The controversy was not about whether helium was found. It was about the irregularity of the signals. Science wants consistency, and cold fusion refused to provide it. The problem of reproducibility. If cold fusion ever comes to life, it will likely be because scientists learned how to control a process that is currently unpredictable. Imagine a chemical reaction that only works 1 out of 20 trials, or a machine that only turns on when the humidity, temperature, pressure, and microscopic texture of its materials align in perfect harmony. That is the challenge researchers face here. Many experiments over the years showed bursts of heat, followed by long periods of silence, radiation spikes that vanished immediately, neutron counts barely above background, electrical anomalies lasting seconds or minutes, sudden changes in pressure inside hydrogen-loaded metals. These results were rarely strong enough to claim a discovery, but they were too unusual to dismiss entirely. Cold fusion became a riddle, too inconsistent to trust, too fascinating to forget. The sensitivity of materials. A hidden variable, a recurring theme across decades of research, is the extreme sensitivity of the results to the physical structure of the materials used. Tiny details that normally do not matter, microscopic cracks, grain size, crystal defects, surface impurities, the alignment of atoms, seem to influence whether any anomalous signals appeared. Imagine baking bread where the exact shape of each grain of flour, the angle at which the yeast cells align, and the invisible imperfections inside the oven walls determine whether your loaf even rises. That is the scale of sensitivity researchers encountered. In some laboratories, heat bursts occurred only when the palladium lattice reached a very high concentration of hydrogen, so high that the metal expanded almost to its limit. In others, the palladium needed to be stretched or compressed. In still others, results only appeared when electric currents passed through the material in specific patterns. This complexity made every success fleeting, every anomaly fragile. Microscopic hotspots, local reactions in a large system. One of the most challenging aspects of cold fusion experiments is that any potential nuclear reactions, if they occur at all, seem to happen in extremely small regions inside the metal lattice. These hotspots might be only nanometers across, present for fractions of a second, surrounded by untouched material, hidden deep inside microfractures or lattice defects. This means that even if a tiny fusion event happens, it might produce only a small burst of heat, a few helium atoms, a minimal perturbation in the surrounding lattice, all of which could be easily missed. In this sense, a cold fusion experiment is not a star, not a runaway reaction, but more like a flicker, a faint pulse, drowned in noise, only traceable when instruments are precise enough. The puzzle of negative results. One of the strongest arguments against cold fusion is that many labs did not observe anything unusual. In fact, most replication attempts failed. But this raises an interesting question. If a phenomenon depends on microscopic conditions inside a complex material, should we expect consistent results at all? For example, superconductivity was once extremely difficult to reproduce. The first transistor designs barely worked except in specific hands. Quantum Hall effects only appear under very narrow conditions. In many fields, early experiments produce mixed results until the underlying mechanisms become clear enough to control. This does not prove cold fusion is real, but it does show that inconsistency does not necessarily equal impossibility. Radiation, a silent, confusing signal. Traditional fusion reactions produce strong radiation, neutrons, gamma rays, and energetic particles. Yet cold fusion experiments typically produce little or none. This absence has long been cited as evidence against nuclear reactions. But some anomalies complicate the picture. A few experiments recorded very low-level neutron bursts. Some detected unusual X-ray emissions. Others captured weak gamma signatures, inconsistent but intriguing. These signals were not strong enough to indicate dangerous nuclear activity. They were subtle, infrequent, and difficult to replicate. Still, their presence, even if rare, raises a quiet question. If something is happening, might it be a nuclear process unlike the ones we already know? A field trapped between possibility and mystery. Cold fusion sits in a unique place in science, too strange to ignore, too irregular to accept, too interesting to fully abandon. For decades, researchers have collected anomalies like tiny puzzle pieces. None complete the picture, but together they suggest a question worth asking. What is these small, stubborn signals are hints of a process we have not yet learned to understand? Science is patient. Mysteries wait quietly, sometimes for centuries, before yielding their secrets. Cold fusion remains one of those mysteries, shimmering at the edge of what might be possible. Section 10. A different kind of fire. Why cold fusion challenges the rules of energy. If cold fusion is real, even in the smallest, quietest form, it would not just be another scientific discovery. It would represent a fundamentally new way that nature organizes energy. To understand why, we must slow down and walk through the foundations of how energy behaves, what fusion normally requires, and why the claims surrounding cold fusion seem to ripple against the known laws of physics like wind across still water. This section explores the deeper physics behind the puzzle, not the controversy, not the arguments, but the question hidden beneath everything. If cold fusion were possible, why would it contradict so much of what we believe is true? To see that, we begin with heat, the simple ancient force that shapes every star, the temperature wall. Why fusion needs a hellfire furnace. Fusion, as we know it today, requires extreme heat, extreme pressure, and extreme density. Inside the sun, temperatures reach 15 million degrees Celsius. At these temperatures, hydrogen atoms move so fast that their positive electrical charges cannot repel each other strongly enough to keep them apart. They collide, fuse, and release energy. This is the core rule of fusion. Heat is not optional. It is the force that overcomes electrical repulsion. The idea of cold fusion, therefore, seems paradoxical. How could two positively charged nuclei merge without the immense violence of stellar heat? It would be like watching two magnets snap together despite both having the same pole. It should not happen under ordinary conditions. This is the reason most scientists initially dismissed the idea outright. The physics, as understood at the time, seemed to forbid it. And yet, experiments kept producing small anomalies that did not fit the expected rules. They were not strong enough to overthrow theory, but they were unusual enough to provoke curiosity. Quantum tunneling, a door that should stay closed. In quantum physics, particles do not behave like solid objects. They behave like waves, and waves can do strange things, including passing through barriers they should not be able to cross. This is called quantum tunneling, and it is essential for normal fusion in stars. Even in the sun's extreme furnace, nuclei still require tunneling to fuse efficiently. But quantum tunneling at room temperature is another matter entirely. Under normal conditions, the probability of fusion via tunneling is so small that it might as well be zero. And yet, some theorists asked, what if the environment inside certain metals changes the probabilities? What if lattice vibrations, electromagnetic fields, or tightly packed hydrogen atoms subtly adjust the rules? This does not violate physics. It simply invokes parts of physics we do not yet fully understand. The idea is controversial, but not impossible. Metal lattices, cages for hydrogen, laboratories for the unknown palladium, the most famous material used in cold fusion experiments, has an extraordinary property. It can absorb vast quantities of hydrogen, up to 900 times its own volume. When hydrogen enters the metal lattice, the atoms arrange themselves into tight, symmetric positions between the palladium atoms. This creates extreme local pressure, altered quantum environments, high electron density, and incredibly short distances between hydrogen nuclei. Some researchers suggest that under these conditions, electrons might screen the positive charge of hydrogen nuclei. Local vibrations, phonons, might force nuclei closer together. Microscopic hotspots might concentrate energy, or quantum tunneling probabilities might increase. If any of this occurs, even at a very low level, it could allow rare fusion events at temperatures far below what stars require. Not enough to power a city, just enough to leave strange little traces, heat pulses, helium atoms, odd radiation spikes. The kind of signals that appeared just long enough to raise questions, then fade before they can answer them. Why chemistry alone cannot explain the anomalies? Some skeptics argue that all observed anomalies, excess heat, helium, radiation, could be caused by chemical or experimental errors. Often, this is correct. Most reported results can be explained by mundane mechanisms, but not all. Some heat bursts are larger than any known chemical reaction can produce. Some helium measurements are correlated too precisely with detected heat. Some radiation spikes occur in patterns too unusual to ignore. These unexplained anomalies are why the topic refuses to die. If cold fusion is ever proven impossible, science must still provide new theories to explain these stubborn observations. In that sense, cold fusion challenges not just physics, but the very process of scientific understanding. The energy equation, why the results, if true, would be extraordinary. A single gram of hydrogen, if fused completely, contains as much energy as dozens of tons of coal. Even a tiny fraction of fusion, microscopic fusion, could produce noticeable heat. This is why some researchers believe the faint heat bursts observed in certain experiments might be nuclear. Their magnitude is too large for chemistry. Their pattern is too erratic for simple heating errors. Their scaling does not match chemical limits. The question is not whether the anomalies require nuclear explanations. Many do not. The question is whether some might. Because even the smallest instance of fusion at low temperature would fundamentally alter our understanding of physics and our technological future. We would no longer rely on stars or reactors to push nuclei together. We would rely on the quiet, subtle rules of the quantum world. A different kind of fire, a gentler one that burns without destroying. A break in the wall of known physics, or an illusion. Cold fusion sits at the boundary where established knowledge meets possible discovery. Not the clean, polished kind of discovery we celebrate in textbooks, but the messy, confusing kind that science often begins with. Strange results, inconsistent data, experiments that behave differently for different people, unexplained blips in instrument readings, bursts of energy that appear only in the right conditions. Some scientists think these signals are illusions. Others think they are clues. The truth may lie somewhere in between. Cold fusion challenges the rules, but only in the same way new fields of physics always have. Revolutions begin with confusion, before clarity takes shape. And so this field continues to exist in a suspended state, neither dead nor fully alive, neither accepted nor debunked, neither scientific nor pseudoscientific. A paradox waiting to be solved. Looking ahead, what happens if the rules break open? If cold fusion is real, it would open doorways to clean, unlimited energy, compact reactors, new forms of quantum control, breakthroughs in materials science, a revised understanding of the atomic world. Not because it replaces current physics, but because it expands its boundaries. Many great discoveries began this way. Superconductivity, quantum entanglement, nuclear fission, the photoelectric effect. All were once considered unlikely or even impossible. Science grows by exploring the edge cases, the exceptions that refuse to disappear. Cold fusion remains one of those exceptions, a whisper in the physics of matter, a possibility that strings together faint anomalies into a single extraordinary question. What if nature is capable of more than we currently imagine? Section 11. The human factor. Perseverance, skepticism, and the quiet search for truth. Science is often portrayed as a purely logical endeavor, a march of data and equations, unaffected by human quirks or biases. Yet history reminds us that every discovery is deeply human, shaped by curiosity, doubt, perseverance, and sometimes stubbornness. In the story of cold fusion, the human factor is inseparable from the science itself. To understand why the field remains alive, against the tide of skepticism, we must slow down and consider the people behind the experiments, the laboratories, and the decades-long dialogue that surrounds them. The early enthusiasts. When Martin Fleischmann and Stanley Pons first announced their results in 1989, the scientific world reacted with shock and incredulity. The press called it a tabletop fusion breakthrough, capable of changing the energy landscape overnight. Yet, the initial excitement quickly collided with reality. Many laboratories could not replicate the findings. Funding agencies withdrew support, and some researchers abandoned the field entirely. But a small group of dedicated scientists remained. They were motivated not by headlines or fame, but by the faint hints of anomalous heat and unexplained phenomena. These early enthusiasts shared a quiet belief: science is not about consensus, but about curiosity. Even if the results seemed impossible, the anomalies were worth understanding. This determination has kept the field alive for over 3 decades. The weight of skepticism. Skepticism is the natural companion of science, and cold fusion has faced more of it than almost any other claim in modern physics. Much of this skepticism stems from the implausibility of low-temperature fusion according to classical physics, the inconsistency and irreproducibility of experimental results, the initial media hype that sensationalized preliminary findings. Skepticism, however, is not merely obstruction. It is a filter. Only claims that withstand rigorous testing, careful measurement, and critical examination survive the scientific process. For cold fusion, the weight of skepticism has been a double-edged sword. It discouraged sloppy experimentation, but it also discouraged risk-taking and slowed open-minded investigation. Interestingly, many researchers who remained in the field learned to work quietly, reporting results with caution and precision. The work became less about fame and more about understanding, a slow, deliberate pursuit of truth. Perseverance in a marginalized field. Working in cold fusion often means working in isolation. Traditional funding sources are scarce. Mainstream journals may reject papers, and peer reviewers can be unforgiving. Yet, for those who continue, the work is deeply rewarding, not for the recognition, but for the challenge itself. The perseverance required is extraordinary. Scientists must design experiments with extreme care, controlling for every possible variable. Learn patience, because meaningful results often appear unpredictably, and embrace uncertainty as a natural part of discovery. Careful approach mirrors the subtle phenomena they are trying to observe. Cold fusion is not a fireworks display. It is a quiet flicker, almost invisible unless one is attuned to its delicate signals. The role of collaboration and shared knowledge. Even in a marginalized field, collaboration has persisted. International conferences, small workshops, and dedicated online forums allow researchers to share techniques, failures, and occasional successes. This network operates quietly, often unnoticed by the broader scientific community, but it is vital for maintaining the continuity of research. Through these collaborations, certain patterns began to emerge. Specific palladium preparations sometimes produced stronger signals. Hydrogen loading ratios correlated with observed anomalies. Instrumentation sensitivity was critical to detecting subtle heat bursts or radiation. By pooling knowledge, researchers slowly build a map of the conditions that might produce measurable effects. This map is incomplete, but it is real, and it represents decades of human ingenuity, patience, and careful observation. The psychological dimension of cold fusion research. Researching a controversial and often ridiculed phenomenon requires mental resilience. Scientists must constantly navigate doubt, both their own and that of their peers. They must confront the possibility that years of work may lead to null results. Yet, they continue, motivated by curiosity and a quiet optimism that nature might still surprise them. This psychological dimension is not trivial. Scientific intuition often guides experimental design in subtle ways. Persevering in a field where the world expects failure requires a careful balance between skepticism and open-mindedness, between caution and creativity. Many researchers describe moments of awe, a brief spike in temperature, a helium measurement that aligns with predictions, or a subtle radiation signal that appears where none should exist. These fleeting moments are enough to sustain decades of labor. A reminder that even in the quietest science, wonder persists. Ethics, responsibility, and the allure of energy. Cold fusion is not merely a scientific puzzle. It is also an ethical one. If real, it could revolutionize energy production, reduce reliance on fossil fuels, and alter global economics. This potential adds weight to the responsibility of researchers. Experiments must be conducted safely. Claims must be reported with caution. Public expectations must be managed carefully. The allure of a revolutionary energy source is powerful, but the human dimension ensures that researchers approach their work thoughtfully, aware of the consequences of both success and premature claims. Science as a human story. Ultimately, the story of cold fusion is a story about humans grappling with uncertainty. It is about the courage to explore the impossible, the patience to observe subtle signals, and the humility to accept ambiguity. Science is not only equations and measurements. It is also perseverance, imagination, and quiet determination. The field may one day reveal something profound, or it may fade into the archive of scientific curiosity. Either way, it demonstrates a fundamental truth. The universe often yields its secrets slowly, and those who seek them must be both careful and persistent, or merely the stubbornly mysterious behavior of materials under unusual conditions. No one knows. The answer remains just out of reach. A horizon that encourages careful observation rather than rushed conclusions. And perhaps this is the most human part of all. The patience to watch, wait, and wonder. Science is not always about certainty. Sometimes it is about attentiveness, about noticing what the universe whispers rather than shouts. Cold fusion, in its quiet elusiveness, teaches us that lesson perfectly. Section 12. The future of cold fusion, hope, technology, and the unknown. As we move into the modern era, cold fusion continues to occupy a peculiar place in science. Neither fully accepted nor entirely dismissed, it exists at the edges of possibility, a quiet frontier where curiosity and caution meet. In this section, we explore the future of this enigmatic field, the technologies that could arise if the phenomenon is real, the research pathways that might reveal its secrets, and the profound questions that remain unanswered. The technology that could transform the world. Imagine a world where cold fusion is proven to work consistently. Even a small, controlled reaction could produce vast amounts of clean energy, minimal radioactive waste, and a practically limitless fuel supply derived from hydrogen. Unlike traditional nuclear fission, cold fusion would not require massive reactors, heavy shielding, or the intense infrastructure needed to contain high-energy reactions. The energy would be quiet, almost imperceptible in scale, yet abundant in effect. A gentle, continuous power source. This technology could transform human society. Cities could run on compact fusion units, reducing reliance on fossil fuels. Remote areas could access energy without building massive infrastructure. Space travel could become far more practical, with lightweight, efficient energy sources powering long-duration missions. Such possibilities make cold fusion one of the most tantalizing ideas in energy research. It promises not just new devices, but a fundamentally new way to interact with energy itself, subtle, controlled, and quiet, much like the experiments that hint at its existence. Modern experimental approaches, today, researchers continue to refine the tools and methods used to investigate cold fusion. Unlike the early days, where results were inconsistent and often anecdotal, modern experiments benefit from advanced nanomaterials that allow precise control of metal lattices, high-sensitivity calorimeters that measure even tiny bursts of heat, sophisticated detectors capable of observing low levels of radiation, and computational models that simulate quantum effects inside metals. These tools have not yet produced universally reproducible cold fusion, but they have allowed scientists to understand the conditions under which anomalies are most likely to appear. Subtle differences in temperature, pressure, lattice defects, and hydrogen loading can now be observed and manipulated with remarkable precision. The field has grown quieter and more meticulous. Researchers no longer chase headlines. Instead, they carefully document every result, positive, negative, or ambiguous, knowing that the truth may reveal itself only after years of patient study. Potential pathways to discovery. Several avenues hold promise for uncovering the secrets of cold fusion. Quantum modeling, using advanced simulations to predict how nuclei might approach each other inside dense metal lattices. Quantum mechanics allows for phenomena like tunneling, which could occur under very specific conditions that are still poorly understood. Material science, engineering metals at the atomic level to create optimal lattices for hydrogen absorption. Tiny imperfections, once considered flaws, may be the key to enabling rare fusion events. Ultra-sensitive measurement, detecting minute temperature fluctuations, helium production, or radiation bursts that occur only in microseconds. Modern sensors can measure phenomena previously invisible to even the most careful experimenters. Interdisciplinary collaboration, combining insights from physics, chemistry, material science, and computational modeling to develop a holistic understanding of what might be happening. These pathways are not quick or guaranteed. They demand patience, precision, and a willingness to follow subtle signals wherever they lead. Qualities that have defined cold fusion research for decades. Challenges that remain. Despite technological advances, cold fusion faces persistent challenges. Reproducibility. The elusive nature of the results makes it difficult to convince the broader scientific community. Even slight differences in materials or environment can affect outcomes. Skepticism. Decades of inconsistent findings have left a legacy of doubt, which continues to influence funding, publication, and collaboration opportunities. Theoretical understanding. Even if anomalous heat and helium production are consistently observed, explaining them within known physics remains an enormous challenge. Any confirmed mechanism could require revising our understanding of nuclear interactions at low energies. These challenges are formidable, but not insurmountable. History shows that many scientific breakthroughs began as anomalies that could not be explained, from superconductivity to quantum entanglement. The human element in the future, as in previous decades. The future of cold fusion depends as much on human persistence as on technology. Researchers must continue to experiment with patience, document results meticulously, maintain ethical standards, and resist the urge for sensationalism. This work requires curiosity tempered with caution, hope tempered with rigor. The field exists in the quiet spaces between possibility and proof, a place where careful observation may one day transform subtle hints into reliable knowledge. The human element is not a hindrance. It is part of the beauty of cold fusion research. It reminds us that science is not just about equations and instruments, but also about dedication, imagination, and the willingness to explore the unknown. Implications beyond energy. If cold fusion is validated, the implications extend beyond energy alone. It could influence climate change mitigation, providing a nearly limitless, clean energy source could reduce greenhouse gas emissions dramatically. Space exploration. Compact, efficient fusion units could make interplanetary travel feasible, powering spacecraft without massive fuel loads. Materials science and quantum mechanics. Understanding the phenomenon could reveal entirely new quantum behaviors in condensed matter, influencing electronics, sensors, and nanotechnology. Philosophy and science. Confirming low-energy nuclear reactions would challenge our assumptions about what is possible in nature, reminding us that even the most improbable phenomena may exist, quietly observable if we know how to look. A quiet hope. The future of cold fusion is uncertain. We do not know whether it will ever be fully realized, or whether it will remain a tantalizing mystery. Yet the possibility itself is enough to inspire continued research, careful experimentation, and patient observation. Cold fusion, if real, represents not a violent revolution, but a subtle, gentle expansion of human understanding. A new way to interact with energy that is quiet, pervasive, and transformative. It may one day allow us to harness the hidden energy of matter without the destructive consequences of current nuclear technology. And even if it remains elusive, it has already taught us something profound. Science is patient. Nature reveals its secrets slowly. Sometimes, the faintest anomalies, whispers in a carefully measured lab, are the ones that guide us toward the most extraordinary discoveries. Section 13. The Quiet Horizon. What cold fusion teaches us about discovery. As we reach the conclusion of this journey through cold fusion, it is worth pausing to reflect not on controversy or disbelief, but on what this quiet, enigmatic field teaches us about the nature of discovery itself. Cold fusion exists in a liminal space, between possibility and proof, between skepticism and wonder, between what we know and what we only suspect. It is a reminder that the universe often whispers before it shouts. The subtle lessons of the unseen. Cold fusion has never been loud or spectacular. Its signals are faint, tiny heat anomalies, small traces of helium, minuscule bursts of radiation. These observations challenge researchers to slow down, to cultivate patience and precision, and to notice patterns that might easily go unnoticed. In this way, cold fusion is as much about cultivating human qualities as it is about physics. The lessons extend beyond laboratories. Observation. Sometimes the smallest deviations from expectation reveal the most. Curiosity. A willingness to explore the improbable can lead to unexpected insights. Patience. Discovery rarely occurs on the first attempt or under the brightest spotlight. Humility. Nature operates on principles that often surpass our intuition, and anomalies remind us to remain open to the unknown. In this sense, cold fusion is less a question of energy and more a meditation on how humans pursue knowledge. It challenges us to be attentive, careful, and open-minded, even when the world expects certainty. The ongoing search. Despite decades of skepticism, small, dedicated communities of researchers continue to explore the phenomenon. They employ advanced instrumentation, nanomaterials, and computational models to refine their experiments. They share data cautiously, building incremental knowledge rather than chasing sensational headlines. This persistence is remarkable not because it guarantees success, but because it reflects the spirit of science at its most patient and contemplative. It is the willingness to follow subtle signals, to explore anomalies, and to respect the possibility that the universe may contain forms of energy or interaction that we have yet to fully comprehend. The philosophical implications. If cold fusion is ultimately validated, its implications will extend far beyond energy technology. It would challenge our assumptions about the limits of physics, the ways in which matter interacts, and the subtle quantum mechanisms that underpin reality. It would demonstrate that the universe holds quiet possibilities, waiting to be revealed to those who observe carefully enough. The discovery would not merely add to human knowledge. It would transform our relationship with the material world, showing that even ordinary substances, under the right conditions, can conceal extraordinary phenomena. Even if cold fusion is never fully realized, the pursuit itself is philosophically valuable. It teaches that science is not only a method for producing reliable data, but a discipline of attentiveness, curiosity, and persistent questioning. It reminds us that our understanding of reality is provisional, always expanding, and often guided by whispers rather than roars. Technology on the horizon. Should cold fusion ever become a practical reality, the technological possibilities are immense. Devices could produce clean, abundant energy from small amounts of hydrogen, revolutionizing transportation, industry, and domestic life. Energy infrastructure could become decentralized, reducing environmental impact and reshaping global economics. Moreover, the techniques developed while investigating cold fusion, advanced sensors, quantum modeling, and precise material engineering will likely have applications far beyond energy, influencing computing, materials science, and even medicine. The pursuit itself drives innovation, regardless of whether the phenomenon is fully understood. A quiet revolution. The story of cold fusion, more than any laboratory result, illustrates a quiet revolution in scientific thought. It is a reminder that progress is not always linear, that discovery is often slow, and that understanding requires both rigor and imagination. The anomalies observed, however fleeting, inconsistent, or small, act as signposts. They guide researchers into territories of knowledge that might otherwise remain unexplored. And in following these faint signals, humanity exercises one of its most distinctive qualities, the capacity to notice subtle patterns, to wonder, and to persist. Cold fusion embodies the tension between impossibility and potential. It exists in the liminal space where physics, philosophy, and human curiosity intersect, a delicate, patient, and persistent exploration of the unknown. This sentence captures the essence of cold fusion, subtle, enigmatic, and quietly transformative. As we close this exploration, it becomes clear that cold fusion is not merely a question of energy, physics, or technology. It is a meditation on discovery itself. It reminds us that the universe often communicates in gentle, almost imperceptible ways, and that understanding requires patience, attentiveness, and humility. Whether cold fusion is ultimately validated or remains an intriguing anomaly, its pursuit illuminates a profound truth about human inquiry. The greatest discoveries often emerge from whispers, from anomalies, and from the quiet persistence of those willing to observe carefully, question deeply, and imagine beyond the limits of the known. In the stillness of laboratories around the world, in the careful measurement of heat, hydrogen, and tiny nuclear signals, science continues its slow, deliberate dance with possibility. And in that dance, we are reminded, the universe is a patient teacher, and those who watch closely may glimpse truths that are as beautiful as they are improbable.